goal. So it's a low-hanging fruit goal. I don't want to be an influencer at all. All right, torque. I really like to do this when I write torque in my notebook. I like to use the T for torque to remind myself that the T for torque is different. So that's the T for torque. Yay, torque. All right, as a reminder, if it's been a while or if we've never heard about torque, both are options, right? Torque is the rotational equivalent to force. So the deal is here that not every force applied to an object is going to create a rotational acceleration. Every force applied to an object is going to add up to the net force that might make it translational acceleration, because we say that all of those forces are acting on the center of mass, even if they're not. We don't actually care where the forces are located. We treat every object in linear world as just this tiny little thing at its center of mass. All the forces act on that thing. So I don't care where the forces actually act. We just assume they act on the center of mass. So location doesn't matter. Direction does. If a force is vertical, it'll create a vertical acceleration. Horizontal acceleration, and some combination in between might make both. But for torque, it actually matters. Now I like to do this as like a real example, but previously I've had classrooms with doors that swung into them. That's not true. So I tried this during first period and I put the forces on that door there, but I was like in the closet and they couldn't actually hear anything that I was saying, so it didn't actually work at all. So this is a door, that's the hinge of the door. I'm going to put 4 forces on it, and we're going to see why it matters, what direction and where the forces are located, right? So I'm going to put one force, F1, straight into the pivot. I'm going to put F2 perpendicular into the door. I'm going to put F3. These are co-located, so they're on the same location on either side of the door. And then I'm going to push directly in on the door for F4. So with your group, I want you to determine, using what you already know about torque possibly, which of these forces are going to be the most effective. So create the most torque, versus which are going to be the least effective and create the least torque. There can be ties. So talk in your groups for just a second and decide which ones rank where.
Is that force just pushing onto the side?
Yeah, it's pushing like directly onto the door. Like if I opened this door and I push this way, you can't see me, but I'm pushing this way.
Okay, so that's...
You can't see it.
Okay.
It's problematic. I need more doors. I'm glued to push on these because I don't think they're on as well. Okay. Making do with a cabinet door that hopefully won't break off, because I actually attached all these cabinet doors during the summer because they were not attached when I got here. So if I apply F4, so that's a force straight into the door, is the door rotating? Nope. If I apply force F1 directly on the hinge but perpendicular, is the door moving? No, absolutely not. I'm going to try F2. I'm going to put it directly in the center perpendicular. Hey, look, that worked. What about F3? I'm going to push on it this way. I'm pushing as hard as I was the first time. It's at an angle, but I'm still pushing. Like you might think, oh, she's just not pushing. No, I'm pushing. So, based on that experimentation, hopefully you got the same answer you got while discussing it. F2 is the greatest, followed by F3, and then F1 is equal to F4, which is equal to 0. So what that tells us is that there are multiple things that determine torque. Torque being the rotational equivalent of force, so therefore determining how much angular acceleration I'm going to experience and how much this object's going to actually rotate. So, 2 things. First is distance from the pivot point. That's the first thing that matters. Typically, we just call this R and go from it. So by just distance from the pivot, F2, F3 have that same distance. And so if that was the only thing that mattered, they would have the same torque. But that clearly didn't happen. And the one that should have the most torque would be F4 because it's the furthest away from the pivot. So clearly this doesn't tell the whole story. There must be something else going on. That something else is the component of the force. Oh, skipped an M. That is perpendicular to the radial line. Ooh, that's a new term. The radial line is just through the object going through the pivot point. So this would be the radial line. Right like that. So the other thing that matters is how much of that force component is perpendicular to that radial line. Only forces that are perpendicular to that radial line can exert a torque. Very similar to work, but for work I needed forces that were parallel to the distance that I was going. Now I need forces that are perpendicular, which is why the equation for torque is equal to F cross product with R. Work was a dot product, which created a cosine. This is a cross product, which means sine. That makes sense because cosine is largest when two things are parallel to each other when the angle is 0. And sine is largest when two things are perpendicular to each other and the angle is 90. So that's really important. So this idea that these are the two things that make up torque is one awesome way to look at torque. So where you think of it as torque is the distance that the force is away from the pivot and how much of the force is in the right direction. That's a way to look at torque. It covers all the things in this equation. The force component, F sine theta, that's the force component. And it also covers distance. But I can also think of it in a second way, and there's a really good reason why I want to do that. Okay? One thing that students struggle with when they think of this is that they really don't actually break down the force component. Okay? If you do that, then do that, and it's fine. But what a lot of students, when they get to torque, want to do is use that equation over there. And so if the question gives them an angle, they're like, that's the angle I must use. I promise that's the right angle. I'm going to use that. I just plug it in for sine theta. That is very rarely true. Occasionally, but not all the time. So to be more careful with this and to really understand what it's saying, there's a second way to think about torque. Instead of a distance and a force component, I'm going to say that the force is just a force. However much. I don't care how much it is, it's just a force. So for example, I have this object located here with its pivot going up this way. And I'm going to apply a force to it. Let's see, maybe this way. That's my force. That's a terrible red marker, but there you go. So the force is just a force. However much I'm pushing on it, that doesn't matter. And instead, we think about the distance. Instead of just saying it's a distance away, we say actually, what's working on this pivot point is not the distance lined up with the radial line, but something else called a moment arm. And that's a way to think of the force is just a force, but how far away it's actually working, the length it's actually working on this object is called the moment arm or a lever arm. It's going to accomplish the exact same goal. Now I leave force alone, and I'm going to think about this distance, r sine theta. That's going to be my moment arm. It's the exact same thing. The equation didn't change at all. Nothing's different. The reason I like to do this is because when you draw a moment arm, you can be 100% certain which angle to use. That's the difference. if you use the moment arm, you can be 100% sure that the angle that you're using is the right one. Okay? So, instead of thinking of this as torque is equal to F times all this stuff, you would think of it as F times a distance. That distance is the moment arm. So let's draw one, shall we? I have this beautiful color here. To draw a moment arm, very important skill to have. I'm going to come around during practice and make sure every single person in the room can do it. That's how important I think it is. So first, I draw a line of action. The line of action is through the force. So that is a line of action. So the line of action is the line on which the force is acting. That's how it got its cool little name. Okay. The moment arm is the shortest distance between the pivot and that line of action. Doesn't matter which way I have to draw it, whatever the shortest distance from the pivot to the line of action is, that's what I'm looking for. One rule, I have to make a 90-degree angle with the line of action. So in this case, my moment arm would be right here. That would be my moment arm. It makes a 90-degree angle with the line of action. It goes from the pivot up to the line of action. That is my moment arm. Here's why this is super helpful. Let's say in this question, I gave you this angle here because I'm being really mean. I gave you that angle there. And you have to decide, okay, can I use that angle? Or do I have to use 90 minus that angle? I don't know. Here's the rule. Once I've drawn the moment arm, whatever angle is opposite it, that's the angle I should plug into the equation. Because r sine theta would be r times the sine of the angle, which will get me the opposite side. So the angle I should be using in my equation is that one right there, which in this case, is it equal to theta or not? It's equal to theta. I can tell from the geometry of it, right? These two are equal angles, even though there's a big rod there in between. The reason I like moment arm, again, is so that I can be 100% certain which angle I should use. Let's do it in an example and see how this works. Then we're going to practice this. So I am tightening a wrench or a lug nut using a wrench. That's what I'm doing. I have a switch pens here. Almost. I have a lug nut. That's going to be my pivot point. I have a wrench. I'm actually really good at drawing wrenches, I've learned today. Like, that's a pretty good wrench. We can all agree that that looks like a wrench, and most of the things I draw don't look like what I'm aiming for. So I feel really proud of my wrench. This wrench makes a 30-degree angle with the horizontal. And I am going to tighten this lug nut by pulling straight down with 100 newtons of force. I'm going to pull down on the end with 100 newtons of force. And my wrench happens to be 20 centimeters long. Again, most students are like, I've got an angle, I've got a distance, I've got a force. Done worrying about it, here I go into the equation. Let's double check with our moment arm really quickly. So, if I'm going to draw a moment arm, I first draw a line of action along the force. And then I want to draw the shortest distance line from the line of action and the pivot point, or between those two things, which in this case is this right here. So this would be my moment arm. So, should I use 30 degrees? No, because it's 30 degrees the angle opposite my moment arm. No. The angle opposite my moment arm would be this one over here, which is 60. So if I solve this problem, the torque is equal to force 100 times radius 0.2 of a meter times the sine of 60, which equals 17 Newton meters. If you don't look really close, Newton meters seems like it's a brand new unit, but if you look a little bit closer, Newton meters also would have been joules. Right? Work is force times distance. This is effectively a force times distance. They're not the same thing. Torque is not a type of energy. So we're going to use Newton meter. Is it positive or negative? I'm twisting down on the wrench. Should this be a positive or a negative torque? Negative. Why? Which way is it going? Well, let's talk about a circular direction. Down's not a circular direction. Clockwise. And clockwise is the negative direction. So I'd get negative 17 Newton meters. Questions about this example? I've made the first two that I've drawn extremely simple, and the moment arm has always been lined up either on the X or Y axis. That does not always happen, so that's a luxury. Prepare for it to not always be true. One other thing, they call the moment arm sometimes the lever arm, and I have absolutely seen questions where they just want that distance. So they don't care about what the force is. They're like, what is the moment arm? Or please rank the moment arms. It doesn't matter what the force being applied is. They're just like, I want to know what that length is. So I would say, okay, that's fine. It's just R sine 60. A question I get asked very quickly is like, but couldn't it also be cosine 30? And the answer is 100% absolutely. The only reason you're not using cosine 30 is because the equation has a sine in it. But if you know what you're doing and you know what distance you're looking for, that moment arm, I don't care how you get it. The reason the torque equation has sine in it is because it's meant to be a cross product, because it's meant to be that force is perpendicular to that radial line. But if you draw this and you figure out that you could also use cosine 30, be my guest. The cosine of 30 and the sine of 60 are exactly the same thing. True statement. 0.707. In fact, why do I know that? Nobody knows. Is that helpful to know in the real world? No. Real world? No. Absolutely not. All right, last thing here. Don't forget that torque is a force applied to an object somewhere away from the pivot point. So I can have gravitational torque. I have gravitational torque anytime the pivot isn't at the center of mass. So, anytime my pivot is not located at the center of mass, there's automatically on every object a force due to gravity. That's occurring on every single object. Whether it's being twisted, whether it's laying flat on the ground, there's always a force due to gravity acting on the object at its center of mass. So if the pivot point's at the center of mass, it's not a big deal because that R would be 0. And so I wouldn't care. But if the pivot point is not at the center of mass, like it wasn't for this wrench, we actually left something off of this question. There is a center of mass, let's say it's exactly halfway, and there is a force due to gravity acting downward at that center of mass as well. If I say this wrench is 0.25 of a kilogram, then I would get this additional piece to that torque. Now, for a lot of questions, it's pretty obvious when they start talking about torque that they don't actually care about the gravitational torque. But then again, in like static equilibrium questions, it's very obvious that they care that the plank had a has a mass and therefore a weight. So be careful with this. Read the question. If it's assumed to be really, really small like this, they probably don't need you to add it in. But technically it was there. It just wasn't part of what they were asking in the question. They were asking what's the torque done by just that one force. If they want the net torque on that wrench, it would have been both of those things. So gravitational torque is applied at the center of mass. So let's do one more example. I have this beam. It's a 500 kilogram beam that is 4 meters in length, and I put a pivot on it right here, 1.2 meters from the edge. So I want to know, what is the gravitational torque acting on this object? As we get into the next class, and we're talking about dynamics, so net torque turns into a net angular acceleration. We go even further, we talk about static equilibrium when that net torque has to be 0. It's going to be important that you remember gravitational torque is always there if the object has a decent sized mass. So the nice thing about it is a lot of the times, unless the object is up at an angle or something, this is pretty simple. If it's a flat object that's resting horizontally, the force is going straight down. That's already perpendicular, so my angle should be 90 degrees. So the torque would be 500 times 9.8 mg times the distance. What's the distance that the center of mass is from the pivot point to this one? Say it again. 0.8. If you need to see it, the sine of theta is 90 because the distance here, that would be the moment arm right there. So it's clearly 1.8 is the moment arm. So if I do that, I don't know, oh, it's 3920. I was about to say, I was forgetting the number, but I didn't. It's 3920. There we go. So, torque is calculated by the distance that the force is away from the pivot and how much of the force is acting perpendicular to the pivot. If that's a little bit tricky when you're trying questions, I highly recommend you drawing that moment arm because it can help you identify what you're looking for when it comes to that r sine theta component. That can be really helpful, okay? Also, all objects that have mass have some gravitational torque. That's why if you're ever